Hi all, welcome to another video of power system analysis based on KTU syllabus. So we were discussing the module 2 of the subject, and today we are going to discuss the unsymmetrical faults on power system through impedance. In the early videos we have discussed the unsymmetrical faults on power system where the faults are considered to be direct short circuits between lines and between one or two lines to the ground. So in that type of fault analysis, the impedance between the fault point is considered as zero. But there may be situations in which the fault path includes an impedance between faulted points. So in these situations, the analysis is carried similar to that of in the previous section, except that the fault impedances are included at appropriate points in the circuits. So first we are going to discuss the single line to ground fault on power system through impedance. So a single line to ground fault at point F in power system through a fault impedance ZF is represented in this figure. So here you can see the fault is occurring at a phase A and it is grounded through an impedance ZF, and other phases, phase B and phase C, are stay as normal. And here from this figure some assumptions can be made, that is the phase current IB is equal to 0, IC is equal to 0, and the fault current, that is means the IA, IF is equal to IA, is flowing to the ground through the impedance ZF. So we can say the voltage VA is equal to IA, the current flowing through the impedance ZF, IA into ZF. Okay, so that are the assumptions we got from the figure, and we are going to find the symmetrical components of the phase current IA, that is IA0, IA1 and IA2. So for that we have to use this matrix. So in that matrix we are substituting the value of IB and IC as 0, 0 here. Okay, and by solving the matrix we will get the equation IA1 is equal to IA2 is equal to IA0 is equal to IA by 3. Okay, IA by 3, which means all the sequence currents are same. Okay, and we can say that IA is equal to 3 into IA1. Okay, and also when we are talking about the voltages, okay, we can express the voltage VA in terms of symmetrical components as VA is equal to VA1 plus VA2 plus VA0, where VA1 is the positive sequence components of voltage VA and VA2 is the negative sequence and VA0 is the zero sequence component. Okay, and from the previous equations, okay, from the previous, that is we know that the VA is equal to ZF into IA, ZF into IA. So if you are substituting that equation here, we can say that VA1 plus VA2 plus VA0 equal to ZF into IA, and also we know that this IA is equal to 3 into IA1. Okay, IA is equal to 3 into IA1. So instead of this IA we can write 3 into IA1. So we will get VA1 plus VA2 plus VA0 is equal to 3 ZF IA1. Okay, so from these equations, that is mainly from this equation, all these currents are same. Okay, so in a circuit the positive sequence, negative sequence and zero sequence currents are same. Okay, which means the same current is flowing through all the sequence impedances. Okay, and also from this equation 4.80 we will get the sum of the symmetrical component is equal to 3 ZF into IA1. Okay, so from that equations we can say that all sequence currents are equal and the sum of sequence voltages equal 3 ZF into IA1. Therefore these equations suggest a series connection of sequence networks through an impedance of 3 ZF. Okay, because all the currents are same. Okay, all the currents are same means the same current is flowing through all the components. Okay, so it is possible only in a series circuit, that we know. Okay, so we can draw the series circuit of sequence networks as like this. Okay, just same as the single line to ground fault of an unloaded generator and all, but the only difference is here we are having an impedance. Okay. So this is the VA1 is the positive sequence component of VA, VA2 is the negative sequence, and VA0 is the zero sequence component. Okay, and corresponding representation here is Z1, Z2, Z0, and the same current IA1, okay, is flowing through all the components. Okay, is IA0 equal to IA1 is equal to IA2. Okay, so this is the corresponding sequence network we will obtain using that equations. Here you can see the impedance representation, that is 3 ZF into IA1. Okay, that is, we know that it is ZF into IA. Okay, the voltage drop across the impedance is ZF into IA. We know IA is equal to 3 into IA1, so 3 into IA1 into ZF. Okay, that you can see here. So the impedance we are taking it as, if IA1 is flowing through that, we are getting the impedance as 3 into ZF here. And from this figure we can write the equation for IA1. Okay, what may be the equation for IA1? So here the voltage is VPF here. Okay, so the equation for IA1 will be VPF divided by all the sum of all the impedances. Okay, sum of all the impedances. So the equation will be like this: IA1 is equal to VPF by Z1 plus Z2 plus Z0 plus 3 into ZF. So Z1 plus Z2 plus Z0 plus 3 into ZF. Okay, all the impedance sum. Okay, so IA1 is equal to like this, and the fault current will be IF. Okay, IF will be IA, we know that. So IA will be 3 into IA1. So 3 into VPF by Z1 plus Z2 plus Z0 plus 3 into ZF. So the symmetrical component of phase A voltages are calculated writing Kirchhoff's laws. Okay, Kirchhoff's laws means we can write the VA0. Here the equation for VA0 will be minus Z0 into IA1. VA2 will be minus Z2 into IA1. And VA1 is equal to VPF minus Z1 into IA1. Okay, that we have written here the corresponding equations. And also we can find the symmetrical component of from the symmetrical component of phase A voltages, the phase voltages VA, VB and VC are calculated using this equation also. Okay, once again I am denoting that the value of A will be 1 angle 120. Okay, I hope all of you clear about the single line to ground fault on a power system through impedance. Thank you.